Right, let me re-explain this slide. So the maximum theoretical is 0.593 for CP, but practically the maximum width that we can go is only 0.4 as written over here. And even when we have taken the maximum practical values of 0.4, when we compare this to the theoretical 0.593, that 0.4 represents only 67%, okay, of the ideal theoretical values, and is 40% of the total power in the wind. So theoretically, we can only extract 59.3% from the incoming wind. Okay, 59.3% of the power from the incoming wind. That is the theoretical value. Practically, we can only extract 67% of the theoretical maximum extractable power. So the practical value of 0.4, the net result is that the practical value of 0.4 represent only 40% of the theoretical power offered by the incoming wind. And can you imagine, only 40% of the incoming wind power can be used to generate wind power that is connected to the electrical grid. And 40% is not a very, it's a fairly high value, but it's still less than half. Okay. So several observations that we can obtain is that when we equate this to this, right, this is what we have derived earlier. When we have obtained our VR, if you recall, when we obtain our VR equals to V1 plus V2 over 2, and then we substitute into our PEX equation. And then if we equate this and this, okay, just to determine what is the value of CP, or what is the relationship of CP, then we obtain this. Okay, so when we equate this and this, we obtain these expressions of CP. Right, expression is the word I'm looking for just now. So we know that CP is equal to this. Okay, so CP depend mainly on the incoming wind velocity and also the outgoing wind velocity. So if you are able to design a wind turbine that can obtain an outgoing wind velocity that is very close to your incoming wind velocity, then you have managed to increase your CP value, and then you have also managed to increase the efficiency of the wind turbine that you're designing. So in short, right, in short, CP is equals to PEX over PW. PW is the wind power, the incoming wind power, okay, which is this term given to us by this term, half rho AV cube. So you simply take this over to the other side of the equation, then you get PEX over PW equals to CP as such. Okay. This is to show you the relationship of torque versus rotational speed. So this vertical line represents torque, and then this horizontal line represents the rotational speed of your wind turbine. So as the rotational speed of your wind turbine increases, the torque increase as well. Okay, and this line represents an incoming speed that is lower than this incoming speed. So this line represents an incoming speed that is higher than this line. So in general, in these two lines shows that as the rotational speed of wind turbine is increasing, the torque that the wind turbine generate also increases, but when it reaches a maximum point, it will drop because the rotors start to fail. And because you cannot have increasing torque forever, go on, that continue to increase forever and ever, you cannot have that. So something has to break down. And this is what we call the locus of the maximum torque, okay, versus the rotational speed. And similarly, you have the power and the rotational speed relationship, and this represents the line where the power is lower than this line. So as you increase the rotational speed, the maximum power also increases until a certain point it drops, and these represent the locus of the maximum power versus rotational speed. Meaning that if you are referring to this operation and you want to extract the maximum power